All right, well, welcome everybody. Welcome back. Those of you who are here in person, great to see you. Those of you watching and engaging online, so sorry about the Zoom error today. It looks like their server's down, and here we are. We're going to be recording this just live from the Fab Lab here. So let's pick up where we left off. We've been discussing the source-free RL circuit. We've been looking at first-order circuits, and now we're looking at the source-free RL circuit. And we started with basic, basic principles. We did a Kirchhoff's voltage loop or KVL loop around the circuit. Express those voltages in terms of the elemental voltages, and across a resistor it's still just Ohm's law, R times I. Across an inductor, however, it's L didt, and we end up with a first order differential equation, separated that, and ended up solving for what current function I of t must satisfy this differential equation. And as you expect, it's an exponential kind of thing. I don't think we said this on Tuesday, but not a surprise that the solution to this differential equation is an exponential function, because exponential functions, the derivatives of them are also exponential functions, right? So it would make sense that you can take r times some function plus L times the derivative of that function. And if that function is exponential, then the derivative is exponential, and you could add some exponentials together to get them to cancel to zero. Right? So all to say, no surprise that the solution ends up being exponential because of their relation between functions and derivatives. We'll see that's true in the second order systems when we get to that point as well. All right, we solved this problem on Tuesday. You can check out the video to watch a walkthrough of that. All right, let's take a look at another problem in in an inductor here. So we've had the switch has been open for a really long time. There's that language we're always looking for, so we know that things have reached steady state, right? So we've reached steady state conditions, and remember that when that happens, as you just reviewed in this last assignment on, I think you're wrapping it up this week on inductors and capacitors, that the inductor becomes a short circuit under steady state conditions, and capacitors become open circuits, or OC for short. We don't have any capacitors here, but we're going to see those as we continue moving on, especially in second order systems where both are present. And so we're looking for I of t, I naught of t, and v naught of t. Ugh, so many things, right? As soon as we find one of those, we should be able to use basic circuit principles to find the others. Okay, and we realize that for t equals greater than 0, that this is a source-free circuit, because that switch opens at t equals, I'm sorry, actually, it closes at t equals t greater than 0, right? Now, I usually get this question, wait a minute, the switch closes at t equals 0, and that means that voltage source is still there. How is this not a driven or forced circuit? But when you look at it, if this is ground, right, it effectively closing the switch effectively grounds this node, right? And so that side of the 3 ohm resistor is ground. Another way you could think about it, if you like visualizing it this way, is that this circuit then becomes decoupled. It's grounded, 10 volt here, the 2 ohm here, and then you have a 3 ohm, a 6 ohm, and the 2 Henry inductor separate, right? Closing that switch breaks those circuits apart. Okay, you can draw them as 2 separate circuits that just happen to share a common ground. Either way you want to think about it, the 10 volt source is definitely not in the picture as far as the inductor is concerned past time t equals 0. Okay, so we can get the initial conditions, or ICs for short, from the no jump conditions. Remember that an inductor, just like a capacitor on our example on Tuesday, the voltage couldn't change abruptly. So from T equals 0 minus to T equals 0 plus, whatever the voltage was on that cap before the switching event occurred, it has to be the voltage on the cap after the switching event, because it's sluggish in responding to changes in voltage. It just can't do it abruptly. It has to take time, and so there's a continuity there. No discontinuity. There's no jumping. Um, and so the inductor, similarly, its current can't change quickly, because if it's magnetized, that magnetism is interacting with the current going through it. That can't change quickly from one moment to the next. It can't jump from one state to the next. So there's continuity there. But whatever the current was in the inductor before the switching event at T equals 0 minus must be what the current is through the inductor at T equals 0 plus. All right, so we can write that out if we want. IL at T equals 0 plus must equal IL at T equals 0 minus. Okay, keep in mind that's for the inductor. The capacitor, of course, its current can jump all it wants. It can change rapidly. Same with the voltage across an inductor, that can change rapidly. But current through an inductor can't change quickly. Voltage across a capacitor can't change quickly. All right, so we know that I of t, if it's source free from t equals 0 plus, or t greater than 0, we know it takes the form I naught e to the minus t over tau. And we know that's true for t is greater than 0. So what do we need? We need to find both I naught and tau. So let's take a look at I naught for, well, actually what we know is that I naught is equal to I of t equals 0 plus, right? Now, I naught is the current through the 6 ohm resistor, right? So to be able to find it, let's go ahead and look at for t equals 0 minus, right before the switching event occurs. Let's draw the circuit. So we have the 10 volt source, the 2 ohm resistor. That switch is open, so we really just have a 3 ohm resistor and a 6 ohm resistor, and the inductor, but the inductor behaves like a short. Right, for t equals, or well, when it's fully charged, or fully magnetized, I should say, under steady state. And so what we can find is IL, so basically all the current is flowing through that shorted inductor. It's going through the 2 ohm and the 3 ohm, and then, oops, hang on here. I'm going to draw this a little bit different. It's coming out of the 10 volt source through the 2 ohm and 3 ohm, and then through that shorted inductor. And so that is IL of t equals 0 minus. We can find that easily. That's IL of t equals 0 minus is just our 10 volts over the 2 plus 3 ohms of resistance. And that is 2 amps of current. So we know then that I naught, hold on here. So I see. This gets kind of confusing. I'm saying I naught, there's a capital I naught, right? So if I of t is the current through the inductor, this is I of t, right? And then in that current, we're referencing the pre-exponential, or the time t equals 0 current I naught, capital I naught. and then there's a lowercase I naught going through the 6 ohm I naught of t. Okay, so just want to be clear what we're talking about here. When we're finding I naught, capital I naught, it's the pre-exponential, the coefficient on the exponential term for I of t current through the inductor, and we've found it because it's equal to IL of t equals 0 plus. But we know by the no jump conditions that's also equal to IL of t equals 0 minus, which we've just found, and so we know that I naught is equal to 2 amps. All right, so there's our I naught. We now need to find tau, which we'll do on the next page. All right, so oops, hang on here. Okay, so IL, so we want to find tau. And so this is for t is greater than 0. And we've got our 10-volt source here now. The switch has been closed, so that 10-volt source and the 2 ohm resistor are just kind of off on their own. And then we've got a 3 ohm resistor, and then the inductor. Try to draw a better inductor. Okay, the 2 Henry inductor, the 6 ohm resistor, and the 3 ohm resistor. And so we want to find tau. So remember that tau is equal to, remember that tau, oops, hang on here. Tau is equal to R Thevenin, I'm sorry, it's L over R Thevenin, where we have to find the Thevenin resistance as seen by the inductor. Okay, and for t is greater than 0, it looks like it's just that 3 ohm and 6 ohm pair, and they're, how are they connected? R Thevenin is what? Looks like it's like a 3 in parallel with 6, right? So we've got a 3 parallel 6, which is equal to 2 ohms. And tau then is, you know, as we said, it's L over R Thevenin, or 2 henries over 2 ohms, or it's 1 second. All right. So IL of t then, we're actually done with. We found the inductor current. IL of t is, we know it's I naught e to the minus t over tau, or this is I naught we found on the last page. It was 2 amps. 2 amps times e to the minus tau is 1, so it's e to the minus t, and that's all in amps. And so there is the answer for IL of t. Before we go on to find the other quantities, I naught and V naught, they're listed here and shown here. Let's pause for a second to just think about the process. We found first, we didn't look for that current through the 6 ohm first, or the voltage across the 3 ohm first, because what's going to dictate kind of how this thing behaves and responds after the switching event is the inductor. The inductor's kind of response to how it's going to let energy back out into the system is what dictates it. So you start with the inductor, and then once you have that determined, then you can go and find the other voltages and currents. We also talked about the fact last time that if you have a source-free circuit, there are, you know, and let's say the energy storage element is discharging, the other elements are going to discharge in the same fashion. So they're going to have the same discharging rate, right? So they're going to be some kind of exponential thing. All right. So so let's take a look at then for to find I naught, little I naught of t, and V naught of t. All right, so here we go. Let's draw the system. So we've got, here's the inductor. Here's this 6 ohm. And then here's the 3 ohm. So we got the 3, the 6, and then the inductor is 2 henries. And let's make sure we draw the directions of the currents that we've been asked to find. We've been asked to find I naught as pointing downwards through the 6 ohm resistor, yeah? So let's actually just draw that a little bit bigger. Okay, and then IL of t, remember that has been shown as going downwards through the 2 Henry inductor. We solved for it based on the direction was shown to us here, going down through the inductor. And when we did our diagrams here, we down in the lower left corner, we looked at coming out of the 10-volt source and then down through the inductor, yeah? In a downwards fashion. So all of our, the directionality is 2 amps is flowing downward, right? Okay, so it's flowing downward and it's dropping off as time goes on, right? Tau is 1 second. So at 1 second, it's going to be 38 point or whatever, 37% or whatever it is of that 2 amps initially. That is the energy source that's pushing current through the 6 ohm and the 3 ohm resistors. And notice that it's actually going to push it upwards through the 6 ohm and the 3 ohm, right? The inductor is the energy source, the thing that's doing the work here in this case. It's going to cause those currents to go upwards, and that's opposite of the direction of I naught. Okay, so what we can say then is, defined by, we can actually, a nice way to go about this, because we have 2 resistive paths and 1 kind of current coming into those paths. Current divider is a great solution here, yeah? So by the current divider equation, we have I naught of t is equal to, it's negative IL of t, again, because it's in the opposite direction, times, well, the branch, it's the other resistive branch that goes in the numerator, yeah? So we put the 3 in the numerator, the sum of the resistive branches in the denominator, and we get a minus 1/3 IL of t, which we already know what IL is, so now we can solve for I naught. It's IL is 2 e to the minus t, right? So it's a negative 2/3 e to the minus t in amps. All right, so we got little I naught. And a couple of ways you could solve for the voltage V naught across the 3 ohm. Remember that that's been defined as positive on this side. I should use better colors. I try to keep things color coded. So we'll go with purple for the voltage. Positive on the left side of the 3 ohm resistor, negative on the other side, right? When we look at that on our diagram here, that ends up being positive on the grounded side and negative on the other side, right? That's sort of V naught. I guess I could write that a little bit better here. So maybe something like this, like V naught of t. A couple ways you could do that. It is in parallel with the 6 ohm resistor. Yeah, the 3 ohm is. So we already have the current through the 6 ohm. And by Ohm's law, the current through the 6 ohm times 6 ohms would give us the voltage across that 6 ohm, right? Which is the voltage across the 3 ohm because they're in parallel at this point. So we could actually write that in here. We could do V naught of t is equal to, well, there's our 6 ohms times, let's see, Oh, you know what? Okay, a couple ways you could do it. You could do it times I naught of t, like this, or you could also do it as times, let me see, how do I make this make sense? Why did I write it that way? Times I naught of t. Oh yeah, no, okay, no, sorry, this is fine. Yeah, and what we're going to do here, because we already know the polarity, we know the polarity is what it is. It's positive on the bottom, negative on the top, because the currents are going in that direction, right? So you can actually just take it, multiply it by the um, the magnitude of I naught of t, because we already know the directionality. Okay, so that ends up being it's 2/3 times 6. 2/3 of 6 is 4. So it's a 4 e to the minus t in volts. And there's V naught of t. You could actually check this another way, or rather, there's another way you could solve for this, but we can check it right now with the fact that the voltage across the inductor is L di dt. Now, this is the current through the inductor, yeah, V dIL dt. The voltage across the inductor is consistent with the polarity of its polarity is consistent with the direction of the current through the inductor. So the polarity across the inductor is actually VL, like this, VL of t in that direction. So when we see it that way, we notice that V naught of t is equal to a negative VL of t. The way that it was drawn in the problem, they drew the problem the way they did with the polarity the way they did across the 3 ohm, right? Because it was dictated that way for us, why we're using, the magnitude of I naught of t, and we're relating this flip to the flipped polarity across the inductor. All right, so then we can go ahead and put that in there. That's a VL of t is, well, it's L di dt, right? L dil dt, and so we can put that in. We know L is 2 henries. We have the current through the inductor. It's 2e to the minus t up here. Take the derivative of that. So we get, well, by chain rule, a minus 2, a negative comes in the front, right? So it's negative 2e to the minus t. That's in amps per second, by the way, if you wanted to keep track of the units, right? The derivative. And it turns out that a henry times an amp per second is a volt. That's how that's got to work if L di dt is to equal voltage, right? So this ends up being a plus 4 e to the minus t in volts, and we see that these two check out. Okay, cool. All right, moving on. Or are there any questions for those of you here? Yeah, John.
Yeah. So when you found I naught t, what happened to the tau?
Yes, right. So even the IL of t, up here, where did my pen go? Up here at this point, yeah. IL of t. Remember, our tau ended up being 1 second. Yeah, yeah. So the tau, the 1, just the t over 1 just ends up, just being the 1. So we get the negative, 2e to the negative t over tau, tau being 1. Yep. Yep. Any other items? Want to just check in on before we move forward? Okay. All right. Really briefly, I'm just going to introduce these, and I can probably put some videos up if you wanted to check out this in more detail, um, there are a couple of really handy functions in systems in being able to test and measure system response. One is called the unit step function. All right. Have you guys seen these before in a like differential equations class or anything? Okay, yeah, a little bit. So you'll definitely see them in further engineering courses, structural dynamics classes, systems courses, control systems theory, and stuff like that. But the unit step function is something that it just simulates a switching event. That something is zero before time t before some time, okay, and it's non-zero after that time. It being a unit step function means it has a magnitude of 1. So you can multiply it by anything if you wanted to say, like, I'm going to represent turning a voltage source on that's equal to 25 volts, and I want it to turn on at t equals 0. So we'll just say 25 u of t, like that. So when you write it like this, that's sort of, I can't write right now, sorry, but okay. You write it like that, u of t, that shouldn't be a mu, that's like a u of t. 25 u of t, basically 25 times the step function, is essentially equivalent to this. 25 volt source with a switch that closes at t equals 0. So it's a shorthand way of writing this switching event. So in circuits anyways, this is how you apply this, right? You can symbolize the fact that switching of elements might not occur at t equals 0. They could happen at some other time. So if it's happening at t naught here, instead it's going to turn on at t naught. Then you just write it as 25 or whatever the voltage is times u of t minus t naught. You just shift that function horizontally towards the right or left. This is a right shift, right? This is just like from basic functions all the way back to, I don't know, pre-calculus or something like that, or calculus. Whenever you start looking at how functions shift in time, maybe even trigonometry when you're looking at phase shift, moving things around. But shifting, so a right shift or a delay is to turn it on later is a u of t minus t naught, right? U of t minus t naught, and there's that delay happening here, coming in later in time. Or if you want to shift, this leftward, or sort of advance this in time, it's u of t plus t naught. Okay, so that's the unit step function. You might see some problems in the homework that have a u of t symbol on there. Sometimes you'll have voltages turn on at different times, like one turns on at t equals 0, another one turns on at t equals 3 or something. It kind of depends. All right. So here they're showing an example. I think we just covered that. Okay. I actually take it back. Sorry. My diagram wasn't quite right. The diagram on the next page is actually more accurate. The value is 0 until, so this would be like a double, or let's see, a two-way switch, a double throw switch. This basically, before t equals 0, it's grounded, so that the voltage here across this is 0 volts, right? And then it's connected, and then at t equals 0, it's connected up to here, and so now it has a value of V naught. Does that make sense? Like this would be A would be if you ground this, right? A is V naught after t equals 0, but before t equals 0, it's actually 0 volts because this is actually pulled down to ground, yeah? Okay, so that's a little bit different than what I drew on the last page, only in that if you were looking at it this way, this node up here would be floating at this point instead of actually grounded, right? So I didn't draw it correctly. It should be like this, okay, where this switch basically goes up at t equals 0. So the value is truly 0. That node is actually grounded. or the voltage across it is 0, whether that voltage source actually has its negative terminal connected to ground is another matter, depending on how the circuit is designed. But okay, last, or well, actually, I think there's 2 other functions. There's a function called the unit impulse function, and it's defined as it's a very sharp ping of a system. So if you've ever walked into a cathedral hall or a church or somewhere that's very echoic or reverberant, and you snapped your fingers or clapped, and you could hear like this echo happening, yeah? In here, you don't hear very much of it because it's not a large space. It's acoustically not that reverberant. But when you do that, you're actually creating an impulse, essentially. You're creating an acoustical pressure wave that is very short in time and 0 before the time it happens, all of a sudden high magnitude, and then 0 again. And that's what an impulse function is. Mathematically, it's something defined that it's 0 for all time before 0, and then it has I think the unit impulse function has a value of it's undefined actually at t equals 0. I'm sorry, the derivative is undefined. Yeah, it's defined as the derivative of the step function, right? So it's actually undefined. It's like infinite at t equals 0 because the unit step function, of course, increases, and du dt is essentially undefined. Yeah, it's like 1 divided by 0, right? Like the 1 over 0. That's the rise over the run. So it's undefined, and then it's 0 for all time after that. So it's super important in systems. It actually turns out I'm fascinated by this topic and love to chat about it. So anytime you want to like explore further conversations, maybe we can do a deeper dive on some of this stuff later. Happy to check in and talk about it. But the impulse function tells you how it, or if you measure the impulse. So this is an impulse function, yeah. Now, if you take a system and you send it an impulse function, a signal delta of t, it turns out, whoops, that's not what I wanted to have happen. Come on, there we go. It turns out that the response of that, let's call that y of t or something like this. The response of that, actually, it ends up being called h of t. You'll learn this in later courses, or maybe you've seen it in a differential equations class or something like that. But h of t is called the impulse response. Okay, it's not a very inventive name. It just means how does the system respond when you ping it with an impulse. Going back to that example of walking into a cathedral or a church and snapping your fingers, what you're listening to when you hear that is the acoustic impulse response of that system. And if you were to measure that, it turns out, like if you had a microphone and you measured its response, it turns out that once you know how a system responds to an impulse, you can actually estimate, in fact, with great precision, and you can, in certain circumstances, you can exactly calculate how it will respond to any signal, no matter what it is. It could be the most complicated signal you could think of add a bunch of sine waves together and then multiply it by a square wave of some other frequency and then shift it up and down and left and flip it around, and whatever the signal is, however complicated it is, if you know what the impulse response of a system is and you have a recorded copy of that, you've measured it somehow, you can calculate how it'll respond to any signal. And that's true. I was giving some acoustical examples, but it's true for anything. It's true for a mass spring damper system in mechanics. It's true for buildings and how they shake. It's true for circuits, how they behave. So super useful function, super cool idea, and you'll actually go in to study this more when you take classes in systems. You're going to cover something called convolution. The convolution function Yeah, it's really cool. Last, there's a function called the unit ramp. It does what it sounds like. It is 0 for all time before the switching event occurs, and then it ramps. It starts to ramp at a slope of 1. It's the integral of the unit step function, and they're useful in doing all kinds of testing. These are used for testing and calibrating codec systems. So analog to digital converters and digital to analog converters or codecs, that kind of thing. Really useful for that kind of work. Okay, so now we can talk about the step response of an RC circuit. And so this is the excitation is a step function or something that turns on at some time. And we're going to kind of sort of derive the response of a step response. I'm going to go through this probably faster than I would if you hadn't seen this ever, but you've kind of done this in physics, E&M, right? This is like an RC charging circuit. And so probably seen the derivation. We want to find, V of t here. Find V of t for t is greater than 0. And so for t is greater than 0, what you have by KVL, you can just add the voltages around the circuit, right? So you have a plus Vs, a minus I times R, and then a minus V, which V is the voltage across the capacitor, right? Is all equal to 0, and that's the voltage we want to derive this formula for. So we have R times I. I'm gonna rewrite this formula here. Okay, so Ri plus V is all equal to Vs. All right, and so all we've done is move the constant Vs to the other side, and now we have R times I. I do want to remind that the current flowing through this thing. Oh, and actually, you know what? Let me back up a second. I think I mentioned that you've seen this derivation done in physics E&M. You may have seen it done all in terms of charge, of how charge is moving around and charge builds up on the plates of the capacitor. And that ends up being, I think, a lengthier derivation than this. We're already taking it at face value that voltage and current, we know how they're related. And we also know that current is in series here. And so the current through the resistor I is the same as the one through the capacitor C. And so we can say that it is equal to C dV dt, right? This simple step here, without having to do it in terms of charge, makes the derivation several steps simpler. Okay, so we end up with our, by plugging that in for I, we end up with an R, and then the I term is C dV dt plus V is all equal to Vs. And there's our first order separable. It still ends up being separable, ordinary differential equation. Okay, now let's talk a little bit about the general form before we actually solve this thing, separate it and solve it. The general form for a forced or step response circuit. So sometimes I'll use the word forced response or driven response. In other words, that there's some other energy source besides the energy storage element that's driving energy to pile onto that element or whatever. Okay, so the general form of this, we actually can write down here. Notice that we have RC there. The general form, RC is tau in a RC circuit, right? So the general form is tau If we're just talking about a generic variable like x, it's tau times the derivative of x plus whatever the function is, x, is equal to the steady state value at x equals infinity. Steady state value at x equals infinity. Okay. I can't remember if I write that down, if I usually cover that after deriving this. I think I do it before deriving it, but let's just, before we even do the derivation, let's just talk about the fact that this variable, Vs, is the voltage at x equals, or at t equals infinity, yeah? And eventually at t equals infinity, the capacitor fills up with charge. No more charge can come onto the plates. So the current drops to zero, right? I drops to zero, then the voltage across the resistor drops to zero, and you have that this node here is pulled up to value Vs, or that there's Vs is the time at infinity, it's the final voltage across the cap. All right, so all to say, we're seeing that show up here in this form. The general form is it's the final steady state value. Okay, so let's separate this thing and integrate to get our work here. So we have an RC dV dt is equal to Vs minus V. All right. Okay. Let's collect the terms with the differential operators. So we'll move the V's with the dV. And so we get a dV over Vs minus V. Okay, hang on here. Let me do this in a couple of steps so we can show how this is going to end up. So we move the Vs minus V over here, right? And then we move, and then we leave the RC over here. Yeah, RC. What am I doing? How am I doing this? RC over dt. Is that? I didn't do that, right? Yeah, it's RC times dt. Yeah, so let's see. So we'd move, dt would come up. Yeah, it would be like 1 over RC times dt, right? Okay, right? That everything got moved correctly, yeah? Okay, so now I'm going to do something that is, all we're going to do is multiply both sides by -1 to put things in a little bit better form. So if we put a -1 on both, we multiply by -1, we get a -1 over RC, and then Vs minus V becomes V minus Vs, right? Okay. All right, so that's what we've done there. And now what we're going to do is integrate. Whoops, that's not the color I wanted. Okay, now we're going to integrate from V naught up to V, and I know I'm not keeping track of my variables and doing this thing exact technical way here. Or that probably didn't make sense what I just said, but we're not expressing our variables in terms of dummy variables, so the limits are different values, but I think we can keep track of what we're doing. So let's just continue with it and make sure we're all on the same page. Ask me if you have any questions. So we're integrating dt from 0 up. When we perform the integration, we have 1 over, there's a 1 over x thing happening here, right? So this ends up being ln of, or rather it's ln of absolute value V minus Vs evaluated from V naught up to V is all equal to a minus 1 over RC times T evaluated from 0 up to T. Again, I'm not using T prime and V prime as I probably should, or something like that, but I think we talked about that on Tuesday. I think we can see where things are going. All right, so so just rewriting what we had this ln Why is this? Why did this do this? Oh no. Okay. All right, PowerPoint has locked up on me in presentation mode. None of my arrow keys work. My pen doesn't do anything. Let's see if I right click. Does that get me out of there? Oh, thank God. All right. Oh, okay. All kinds of technical difficulties today. Never a dull moment. All right, so ln, I'm just going to rewrite what we had on the last page there. ln of, this gets a little messy for a second. ln of v minus vs evaluated from v naught up to v is equal to minus 1 over RC times t evaluated from 0 up to t. Okay, we're going to go ahead and take the raise RC, 1 over RC. Oh, okay. Yeah, sorry. That's the R didn't get its tail there. So we're gonna do an e to the both sides. And then we'll plug in the limits at the same time. So we get an e to the ln of, when we evaluate at v and v naught, we get a v minus vs over a v naught minus vs is equal to an e to the minus 1 over RC times t. We know that e to the ln of anything is just that thing back, yeah? So we get v minus vs over v naught minus vs is e to the minus 1 over RC times t. And actually, I'm going to rewrite, well, I'll just rewrite it another step here. So this is v minus vs. We're going to multiply that v naught minus vs up to the right side. E to the minus 1 over RC times t. And finally, we can solve for v. It's on the left there. That's what we want to find here. V of t is equal to, we add on a vs plus v naught minus vs. Yeah, nice. All times e to the minus 1 over RC times t. Okay, that's our final formula. And let's actually take note of what each of these terms are on here. Vs is v at infinity. It's the steady state value. V naught is the initial cap voltage. In this case, and tau is, tau is equal to RC. We put in the RC is the constant. So this V naught minus Vs term right here, that's actually the difference between the initial cap voltage and where the steady state value is going to. We were to draw this on where my slides are going here. Oh, okay, here I've got this on the next slide. All right, so V of t. So you see this? This is the steady state here. It's V at infinity. Here's the initial cap voltage. So you can see this is coming out the initial cap voltage, V naught. This difference here, that is the steady state value minus, well, actually it's, well, the magnitude of it is V naught, V of infinity minus V naught, yeah? And that's That's that difference here. You see that? So this could be 0, right? When this is 0, when the cap is initially uncharged, what you're going to get is this. What you're going to, what you get. Like, so if for v naught equals 0, 0, you're going to find something like v of t is equal to v at infinity minus v at infinity e to the minus t over tau. Or you can also write it as like v at infinity times 1 minus e to the minus t over tau. And maybe you've seen it that way in like physics class, right? The form that we've shown it here is the general form, the complete response rather. And so the complete response to any system is always the steady state response plus the transient response. So the steady state is where things go to under steady state conditions or DC conditions. Transient response. Have you guys heard of the word transient before? Or like transient response? It essentially means what happens in a short, brief time between one state and the next. And that's kind of what's going on here. This right here is the transient response. Okay? And so what we're seeing here is kind of like there's the transient response. That's actually like that's the natural response. And you add on the steady state conditions, and that's the complete response. This idea will stick with us as we go into second order systems, where the transient response can start to do some more fun things, like if it's going towards some steady state value, it can overshoot that and then kind of oscillatory die down to that steady state value. Sometimes we call that ringing, or you've experienced this with like a spring, a mass on a spring. If you bounce the spring, the mass on the spring bounces up and down for a while, and then it starts to slow, and then it's coming to some relaxed length, some relaxed position. A building shaking, in an earthquake, will do that. All right, so okay, so let's see if we can get this example problem in here. In a few minutes, we've got more than 10 minutes, and maybe we can do that. Hang on here. Okay, so although I think this one's a little bit longer, but okay, the switch has been at position A for a really long time. All right, we know things have reached steady state value. And then it moves to position B at t equals 0. We want to find V of t, that voltage across the capacitor, for t is equal to 0. So that long time lets us use the steady state conditions, which will recall that the capacitor behaves like an open circuit. So what we want to do is find, we have those no jump conditions. There's no jump conditions where VC of 0 plus, rather, because that's what we want to eventually find, is the initial voltage on the cap, right? VC of 0 plus is equal to VC of 0 minus because of that no jump clause or condition. So we know that this thing is, when the switch does move to point B, all right, before we solve this, let's take a look at it. The capacitor is going to be, it's in position A for a really long time. This eventually goes open circuit, the capacitor does, yeah? And then no current is flowing through here, so all the current is going through the 3K, 5K series. They're basically in series at that point because they're carrying the same current. There is this connection over to the capacitor, but it's full. Now it's an open circuit, you can take it out. can imagine it not being there. How do you find the voltage across this? Trusty friend voltage divider. Voltage divider, find the voltage across the 5K, that's the voltage across the cap. So we know that VC of 0 minus has some non-zero value, it's charged up to something. VC of 0 plus, try to capture this here for the video. VC of 0 plus has to be whatever that is, yeah? So when we switch from A to B, it's starting out at some value, and it's going to charge up to some new value. Now let's look at where it's going to go. Is it going to go up or is it going to go down? Well, take a look at the voltages. This is 24 volts. Okay, divide that down. Whatever is across this 5K, it's going to be less than 24, right? Voltage divider always divides, always siphons some off. Okay, we're going to lose something across the 3K. So this is going to be less than 24. We put it in this position B. Okay, now it's connected through a 4K resistor to a 30 volt source. And it's going to start charging towards that 30 volts. The 30 volt source is going to push current through the 4K onto the plates of the cap because it was at something less than 30, yeah, whatever this was. And it's going to start charging this thing up to 30 volts. Eventually, the cap will become full, and it'll be at 30 volts. No current will flow through the 4K anymore. All right, see the picture of like the step-by-step what's going to happen before we go into solving anything. Does that bring up any thoughts, questions? Going through that thought process, something as I think the skill I recommend you continue to sharpen, because looking at it in its entirety, it's kind of like, whoa, there's a lot of stuff happening. There's a capacitor, there's other voltages and stuff. Breaking it down and doing these time-stamped kind of snapshots, little snippets of a movie that's going to happen, right before things, what happens at t equals minus, negative t is less than 0. You kind of get a picture, a little movie of what's going to happen. This thing fills up. Switch that over, and now you've got a little bit of a new movie in your mind of what's going to occur. Very helpful to do before you put pen to paper. All right, so let's put pen to paper, or stylus to screen.
Should we like logically out of it without math? So just with math, but without like hard math. So just looking at the fact that it's currently on the 24 volt circuit. So using the voltage there to find our, VC
0 minus,
yeah,
which must be also 0 plus.
Exactly.
Yep.
So basically it's just use that, solve for that, and then logically, once it flips over, the 0 minus is going to have to be less than 0 plus inherently because VC on that side,
you're saying all the right things, except VC of 0 plus has to be equal to.
Yeah, but the individual components of.
Well, across the cap, going from A to B, the voltage can't change abruptly at all. It has to stay exactly the same. So when you solve it for t equals 0 minus, you know what the voltage across the cap is? When that switch moves over, even though now it's connected to some other source, this could be 1 billion volts. It doesn't matter how much electric, quote, pressure this thing is putting onto the cap to change its voltage. The capacitor will not change its voltage instantaneously. It has to gradually go to there, so it takes a finite time to get to there. So the voltages will be equal. VC of 0 plus right after the switching event will be exactly equal to VC of 0 minus. Okay. Yep. And then it charges up to, in this case, to whatever the other voltage is. If there was some other configuration there, like, I don't know, there was like a resistor there, then you'd have a similar kind of voltage dividing thing. It'd be some fraction of 30 volts. Okay. All right, well, let's take a look at, let's just check out. So for, we know that V naught is from the initial conditions. Okay, and I'm sort of spelling that out because it'll help us as we get into the second order systems. It gets more involved at that point. But all right, so we've got this 24 volt source. There's the 3K, there's the 5K, 3K, the 5K, and then VC is open. And so that's VC of t equals 0 minus. And so we can find VC of t equals 0 minus. Whoops. We're being very meticulous with our notation here so that we're showing whether it's t equals 0 minus or 0 plus or whatever, so we can show the process. Well, by voltage divider, it's 24 volts times 5K over 3K plus 5K. You could leave the K's off if you want, but I'm just putting them there so we see where they're coming from. It ends up being 15 volts. Nice. So, so V naught is equal to VC of t equals 0 plus, but that by the capacitor's behavior has to be equal to V of t equals 0 minus, which we just found is 15 volts. All right. Last thing we need to do is find we need to find tau. So we need to find tau. Remember that tau is going to be equal to R Thevenin times C for time greater than 0 after the switching event occurs, because that's when the transient portion is happening, when the capacitor is changing from one state to another. So we draw in that circuit here. This is, oops, didn't know that right. Here's the cap. Here's the, what is this, a 4K or whatever. And then here's the 30 volt source. And we want to find our Thevenin. Remember, that's the Thevenin resistance that the cap sees looking into the 4K 30 volt source. That's a simple one. It's a 4K in series with a 30 volt source. That this circuit is already kind of Thevenized, if you catch my drift, right? A Thevenin circuit is a one resistor in series with a one voltage source, right? So if it were more complicated than that, we'd need to find the Thevenin resistance, but it's not more complicated than that. It's already kind of Thevenized. So we have then that R Thevenin is equal to 4K, 4 kilo ohms. All right, so basically, I think we're done at this point. So tau is 4 kilo ohms times 0.5 millifarads. Kilo times a milli is 1. So tau is 4 times a half, which is 2 seconds. And then I think we can put in for the formula at this point, right? We've got, hopefully this doesn't freeze. Okay. Per second? Oh, yeah. Oh, gotcha. Yeah, yeah. Yep. Yep. Okay. And so last, if we're following the process, right? We kind of already know. We talked about where this is going already. We actually kind of already know V at infinity, right? We want to find V at infinity. We sort of talked about this already, but in terms of outlining the steps that you need to follow, that we need to follow in solving these problems, and again, getting familiar with the process, the method, even if it's simple and straightforward now, keep that with you, because the second order systems, there's a lot more stuff to find, and it's very process oriented or methodical. And so getting used to it now at the first order level will make the second order systems much, much easier for you to navigate. All right, so we've got that 30 volts, 4K, and we kind of already know just by inspection, just looking at it, you can see that V at infinity is eventually going to charge to 30 volts. Right, this is for t is larger than 0. And so now we just plug everything in. We've now found, we've got V naught is 15 volts, V at infinity is 30 volts, tau is 2 seconds. And so we have everything to plug into the general formula. We've got the general formula again, which we derived shortly ago, is, hang on here, V at infinity plus V naught minus V at infinity e to the minus t over tau. And so what do we get? We get this is, let's just point out here that this is V naught is 15, right? And V at infinity is 30. And so here's what, and this is 30 volts, right? So here's what we end up getting. V of t is equal to 30 volts minus 15 e to the minus t over tau. Let's think about what that function looks like. So here's the voltage versus time, right? Let's draw the first function. Let's say we'll draw it in red or something. 30 volts is just a line, right? It's not much of a function at all. It's just a DC value. Minus 15 e to the minus t over tau. Okay, so 15, let's just look at this. 15 e to the minus t over tau, what does that look like? It looks like something that starts at 15 volts and then dies off as time goes on, yeah? But we have minus 15 e to the minus t over tau, so it's flipped. So it's 30 minus that amount. So we just take this and then, right? So that's what that function looks like. It starts out at 15 volts. It's going to arrive at basically 67% of, you can show this. We didn't actually do this for the charging circuit, but it's going to get to 67% of the difference. Well, it's going to get for 15 volts plus 67% of, or basically about 2/3 of the way, 2/3 of 15 volts closer to 30 volts at t equals 2 seconds. Right, this is tau. That makes sense? We didn't cover that extensively, but so let me just take a look and see what else we had to cover. Basically, that's it. So there was one more example problem I was going to do on an inductor circuit, and I will have to do that next week. I think that's what's going to have to happen. We can do that on Tuesday when we get together. There's one more example problem on a that I don't think I'm going to get to be able to do today. So that concludes today's session, at least. I will post this video. And it should be up later this evening. All right. Have an excellent weekend, all, and apologies again for everybody watching online. Zoom their server totally crashed or something. So check in with me after you've watched this video, and I look forward to see you on next Tuesday. And until then.